Now let's go through our approach to trig functions, right? So firstly, we want to determine which quadrant the trigonometric point lies in. Then we want to identify the first quadrant base, or the symmetric point lying in the first quadrant. Then we want to use ASTC or cast to determine the sign, whether it's negative or positive value. Then we want to evaluate the required value exactly if able to from exact trig values. Alright, let's go through an example now. So, as I said before, make sure you guys pause the recording, have a go at these, and then watch the solutions. So, what we're going to do is start with part A. So we want to find the cos of 5 pi on 3. So, of course, this is in our second quadrant. Oh no, sorry, this is not in our second quadrant. So it's greater than 1 pi, right? And it's 5 pi on 3. So we almost have 2 pi there, right? Because 2 pi would be 6 pi on 3. So we actually have something that is around about here. So what we want to do is we want to find the equivalent angle. So let's go back to our last slides. Remember that in our fourth quadrant we have 2 pi minus theta. So we know that 5 pi over 3 is equal to 2 pi minus theta, and this gives us that theta is equal to pi over 3. So this angle in here is equal to pi on 3. So let's apply our cast. So we know that the cos of 5 pi on 3 is going to be positive because it's in that positive C quadrant. And we know that it is going to be equal to 5 pi on 3 is going to be equal to the cos of pi over 3. So let's find the cos of pi on 3. So pi on 3 is going to be down here on our special triangle. Pop in our sides, right? The cos is the adjacent over the hypotenuse, which is 1 on 2. And that is our answer. Now moving on to the sine of 7 pi over 6. So this is a little bit more than 1 pi. So 1 pi would be 6 pi and 6. It's a little bit more, which means that this angle is somewhere around here. So let's draw in cast. We know that sine here is going to be negative because the only trig ratio in the third quadrant that's positive is tan. So let's figure out what our angle is. So going back, we know that in our third quadrant it is pi plus theta. So we know that 7 pi over 6 is equal to pi plus theta, which gives us that theta is equal to pi over 6. So drawing that in, get pi over 6 here. So we know that the sine of 7 pi over 6 is equal to the negative of sine pi on 6. And remember, we need that negative because we know that the sine of 7 pi on 6 is negative because it's in that t quadrant, but the sine of pi on 6 is positive because it's in that a quadrant. So we need to pop that negative in there. Now let's find the sine of pi on 6. Remember, pi on 6 is up here on our special triangle. Sine is opposite over hypotenuse, which is 1 over 2. So this is negative a half. Alright, let's move on to our next example. So here we have the tan of negative 30. So this is going to be a clockwise 30 degrees. And we want to determine what that looks like. So in that quadrant, tan is going to be negative because it's in the C quadrant, which means that our equivalent angle, 30 degrees up here, which is symmetrical, is going to be the negative. So tan of negative 30 is going to be the negative of tan 30. So 30 degrees is equal to pi on 6. You could do that using the radian degree the formula for changing radians to degrees and degrees to radians. But when you kind of get more practice using these, you kind of remember the simple conversion. So 30 degrees is pi on 6 radians, and so forth, because those are ones you commonly use, right? So tan of pi on 6. So tan is equal to opposite over adjacent, which gives us negative 1 on root 3, because our opposite is 1 and our adjacent is root 3. Alright, so this is how we found our exact values of angles outside of the first quadrant using our symmetry properties. Now let's get on to solving some trig equations. So again, make sure you pause the recording and have a go at this yourself. But here we need to find the solutions of 2 sine squared x plus cos x take 2 equals 0 between 0 and 2 pi. So what we need to remember to solve this equation is actually our Pythagorean theorem. So remember the Pythagorean theorem that we learnt, where we had sine squared theta plus cos squared theta equals 1. Right, we learnt previously in the lecture. So right here what we can do is we can go 2 sine squared theta is actually equal to 1 minus cos squared theta. So we have 1 minus cos squared theta plus cos, sorry, I'll put in x. Plus cos x take 2 equals 0. Now, how do you think we could further solve this? We have 2 minus 2 cos squared x plus cos x take 2 So we have gotten rid of our 2's because they cancel each other out. And we are left with negative 2 cos squared x plus cos x. Now, there is actually I guess, two ways that you could solve this, depending on what you have here. If we had another value, a constant value, such as +4 or +5 or something, it would actually be it would actually be a bit of a different story. If you are, if you're wanting to try something new with algebra, I'd recommend trying to solve this equation where you have a plus, a number added on the end. I'll go through that in a second after I've gone through how to solve this equation right here. All right, so for this one here, what we can actually do is factorize out cos x and use the null factor theorem. So this is a similar situation to if we had, 2 y squared plus y equals 0. How would you solve that? You just factorize out y and use null factor theorem. And that's exactly what we're doing here. So we know that cos of x equals 0, or negative 2 cos x plus 1 equals 0. So between 0 and 2 pi, right, cos of x equals 0 when our x values are 0, right? I don't mean our x value here. I mean like our x value on the unit circle, right? So these are going to be 0 on the y-axis, right? So the angles are going to be pi on 2 and 3 pi on 2. Now we need to solve the rest of this equation here. So we're going to have cos x equals a half. So we just took that 1 and that negative 2 over to the other side. Now we need to figure out when is cos of x going to be equal to a half. So here we need to use our special triangles or our table of values. So our special triangle that has a half in it is this one here. So we're going to have root 3, 2, 1. Cos is equal to a half when we have the adjacent over the hypotenuse. So this is going to be when x is equal to pi over 3. Now, let's have a think about if there are any symmetric properties that we can also apply here. So we know that pi on 3 is a solution, but x is also going to have a positive value, not just in this first quadrant, but also in the fourth quadrant. So we're going to need to find the equivalent angle here, right? And that is going to be equal to 2 pi on 3, to 2 pi minus pi on 3, right? Which is equal to 5 pi on 3. Alright, so that was our solution for this question here. A little bit complicated, but nothing you wouldn't expect to come across. So all we did is we used our Pythagorean identity and substituted that in for sine squared x, so that our equation was only in terms of cos instead of being in terms of both sine and cos. Once we did that, we factorized out cos x and used the null factor theorem to solve for each of those factors. When we got that cos x equals 0, we used our axes to determine at what angles those would be. Then when we got the cos equal to half, we used our special triangle to find out those values, including the use of any symmetry properties, because we knew that cos could also have a positive value of a half in the fourth quadrant as well as in the first quadrant. Alright, now let's get on to graphing trig functions. So, let's take the graph y equals a function of bx plus c plus d. Right? What do you think all of these letters, a, b, c, and d, might mean for our function? Pause the recording and have a think about it. So, we have a dilation factor of the absolute value, which means the positive value of a, from the x-axis parallel to the y-axis. Right? So this means a dilation factor means that our function is being stretched. And if our dilation factor is parallel to the y-axis, it means that it's being stretched upwards. Right? It's being stretched vertically. It's not being stretched outwards, it's being stretched vertically. Then we have a reflection in the x-axis if a is negative. So if a is negative, it means that our function is actually being flipped in the x-axis. So, say our function looks like this. If we made that a negative, it would be flipped up like this, be reflected. Alright, that was a terrible drawing, but you understand my meaning. There is a dilation factor of 1 over b when b is negative. This dilation is from the y-axis parallel to the x-axis. So this is where our function is being excuse me, is being stretched out horizontally. Right? Okay. We have a horizontal translation of c units to the left if c is greater than 0, or to the right if c is less than 0. We have a vertical translation of d units up if d is greater than 0, or a vertical translation of d units down if d is less than 0. So, we basically assume that for our function of sine, where we have y equals a sine of b, then in brackets x plus c plus d, is the image of the basic y equals sine x graph after the same set of transformations are applied. What this essentially means is that most of the time we can look at the translations occurring A, B, C, and D and apply them to our basic y equals sine x graph to get our graph. However, the period, amplitude, and equilibrium, or the mean is what we also call it, position of trigonometric graphs are key features that may or may not change. So, hopefully you're a little bit familiar with what these terms mean. The period is the time taken for one revolution. The amplitude is the distance between the middle of the graph to the top of the graph or the bottom. And the equilibrium is the middle. So, just drawing a quick diagram, say we have a simple sine curve like this. One period is this distance here because this is one revolution. Our equilibrium is this line here. And our amplitude is this distance between the equilibrium or the middle and the top, or alternatively between the middle and the bottom. So this is amplitude, amplitude, and this is our period t. All right. So, this is a quick summary of all of these terms. So, the graphs of y equals a sine of bx plus d and a cos bx plus d have the following features. The amplitude is equal to the absolute value of that coefficient of sine or cos, which is a, and the graph is inverted so that a is less than 0. So if a is negative, then the graph is inverted or flipped around the x-axis. Our functions have a period of 2 pi over b. So to find the period, you're going to want to divide 2 pi by the absolute value of b. And then our equilibrium position, that's our equilibrium line. So this dotted line here is at y equals d. So to find the equilibrium position, you just need to look at what the d value is, and that will be it. To find the range, our lower value is going to be d minus a, and our upper value is going to be d plus a. So of course, going from d minus a will get us to down here, and d plus a will get us up here. So this gives us the full range. All right. So let's get on to an example. So here we need to sketch y equals 4 minus 2 sine 3x between negative pi on 2 and 3 pi on 2. So, let's get started. We know that our a value is negative 2, so our amplitude is 2. We know that our d value is 4, and we know that our b value is 3, meaning that our period is going to be 2 pi over 3. Alright? So, let's quickly sketch this out. Negative pi on 2. So if this is y, this is x, right? We know that our equilibrium line is going to occur at 4. So this is the equilibrium line that our curve will sit on. And our amplitude is 2. So our curve will be going up to here and down to the x-axis here. And our period is 2 pi on 3. The other thing we know is that our curve is flipped because it has a negative coefficient. So our regular sine curve looks like this, but this is going to be flipped. So it's going to look like this. Right? So let's get started on sketching our curve. So our curve is going to start on the y-axis, and it's going to go down and back up again, right? The period is 2 pi over 3, right? And we want to go up to a maximum of 3 pi on 2. So 3 pi on 2 is half pi, and 2 pi on 3 is about like 0.7 pi, approximately. Let's check that. Yeah. So we don't actually need to draw the full, we need to draw a little bit more than a full period, because our period lasts only 0.7 pi, whereas we need to draw up to 1.5 pi. So what I'm going to do is draw to approximately 2 periods. Now let's think about what's happening on the other side. We need to go down to negative a half pi, so it's going to be a little bit less than half of a period. So we go up, and then maybe we'll stop about there. Alright. As you can see, our equilibrium line is at 4. Our amplitude is at 2. Actually, I just realized that was a mistake. This shouldn't go all the way. Sorry about that. So it needs to go more like this. It shouldn't be touching the x-axis. But yeah, and this is what our curve is going to look like. Alright, now let's get on to phase changes. So remember when we were going through plus c's in with the x's and how these are horizontal shifts. So if we have y equals sine of x plus c, this has a phase shift of negative c from the graph y equals sine x. Right? If we have a graph of y equals sine of x plus c, this also has a phase shift of negative c from the graph of y equals cos x. So as you might have seen, cos and sine x actually look very similar functions, and that is actually because they are, right? They're exactly the same function, except with a phase shift difference. So one is just moved a little bit along the x-axis, right? So as you can see here, in the blue, we have y equals sine x, and then we moved this to the right by pi on 4, because we had negative pi on 4. Remember, even though it's a negative, it actually moves it to the right. And this is our new curve. And as you can see, whereas before it started at 0, it's now starting at pi on 4. It intercepts here at pi, it's intercepting here pi on 4 later. 2 pi, pi on 4 later, and so forth. Alright, now let's get on to another example. So here we want to sketch the graph of y equals 2 cos x minus pi on 4 between 0 and 2 pi. So what we have here is a graph with an amplitude of root 2, with a phase shift to the right of pi on 4 units. So let's start by writing out what we know. We know that the amplitude is root 2. We know that it's going to be along that x-axis because we don't have a horizontal shift. And we also know that it's a positive cos function. So our original function is going to look like this, right? Our period is going to be 2 pi because b here is just 1, so it's going to end here. Now we want to move this to the right by pi on 4, right? So what we want to do is think about this intercept is going to happen pi on 4 later. This intercept is going to happen pi on 4 later. So we know that it's going to look like this, right? And then we just need to figure out where it's going to end up on that y-axis. Now, because it has moved forward, we're actually going to see more of it, right? So it's actually going to look a little bit like that. All right. Obviously, we have not sketched that exactly, so what we're going to do now is actually pop in a few of the values. So, we know that the amplitude is root 2. The minimum value is going to happen at negative root 2. And then let's pop in our intercepts. So typically, y equals cos x has a value of 0 when our angle is pi on 2. Right, so this is going to be pi on 2, and then 3 pi on 2. But because we have moved pi on 4 to the right, what we're going to do is add pi on 4. So we're going to have pi on 2 plus pi on 4, which is going to give us 3 pi on 4, and so forth. Alright, now let's get on to our next few questions. So here we're going to be solving some trig equations. So, for this one here, we're going to solve for x. Again, pause the recording, have a go at this one before I go through the solution. So, here we have root 3 sine x equals cos x. What we actually need to do here, whenever you're given an equation where you have both sine and cos, and you can't do anything with the Pythagorean identity, what you typically need to do is actually make this into a tan equation, right? So we are going to have sine x over cos x equals 1 over root 3, which gives us tan x equals 1 over root 3. Let's draw our special triangle. Way around, sorry. So we're going to have pi on 6 here and pi on 3 here. Other way around, sorry. Pi on 3 and pi on 6. So our tan, remember, is equal to our opposite over adjacent. So x here is going to be pi on 6. Now let's see if we have any symmetric properties. So we're going to have cast. So tan is also going to be positive. Or tan can also be positive 1 on root 3 in the third quadrant here. So we know that this value here needs to be pi on 6. So this can also be 7 pi over 6. Alright. For this equation here, we have actually solved this previously in the lecture if you want to go back to that and try that.